Hello everybody. This is a continuation of what we've learned so far in Chapter 11. Okay, so far what we've done is define axis of rotation for circular motion. We've defined angle, and as using the variable theta, angular speed, omega is equal to d theta dt, angular acceleration, alpha is equal to d omega dt. And then we've defined positive and negative rotational direction using a right-hand rule. And recall that that rule is putting your thumb in the direction of the axis and your fingers wrap around the direction of positive motion, which is counterclockwise for positive motion about a certain axis. So since we've already defined counterclockwise as positive rotation, we can use that same convention to treat all of our circular motion quantities as vectors, such as angular velocity and angular acceleration rather than speed and acceleration. So this is showing rotation about the z-axis, which would give us quantities of d theta dt k hat and d omega dt k hat as shown. So if these quantities were positive quantities, then what that means is if you put your thumb in the direction of the z-axis shown, motion would be in the counterclockwise direction. Now what I'd like to talk about is something called centripetal acceleration. And we're going to kind of go through the steps graphically to show what this is. So it isn't really a derivation, it's more of an explanation of what centripetal acceleration is. So we're going to start out with a circle and imagine motion around this circle, motion about the axis coming out of the page. If we call that axis the z-axis, then we're going to talk about motion about the z-axis. So we're going to start out with something called a tangential velocity. And what that means is speed with direction tangent to the circle at all points. So basically moving around the circular path. So you can imagine a car driving around a curved path, and the curved path is the shape of this circle. And so at some time later in the motion, we've got v1 as our vector for velocity. And as you can see, that also is tangent to the circle. So you can imagine going completely around the circle how these vectors would look. We're going to define angle theta. So now this is the angle that is swept out at any given time. So you can imagine the car or whatever object is moving around the circle has a string attached to it that leads to the center of the circle that it's rotating around. And you can imagine that that string paints out a path and sweeps out a certain angle shape. That angle is theta. And so, due to the fact that these two vectors are at 90 degrees to the radius, as shown, we can see that theta is also the angle between the two vectors. And so now what we're going to do is we're going to move everything down so that we can take a look at the geometry here. Okay, now we see that not only is the angle theta still the same as what we showed, but also these are alternate interior angles. And so theta is still the angle between these two vectors. Now what we want to do is we want to find out what delta V is. Well, delta V is V1 minus V0. And recall that in order to subtract vectors graphically, we need to take the negative of one of the vectors as shown. So now we can do tip to tail and add these two vectors in order to get the difference between them. So doing that, we end up with delta V as a vector, and we can see what the direction of delta V is here graphically. And if we were to bring delta v back up to the circle, we notice that delta v, if we take it from the center of the motion here, between the two velocity vectors, points toward the center of the circle. And that is the case at all points. Delta v will point toward the center of the circle here, as long as we have uniform circular motion, meaning motion with constant tangential speed. What we're going to do is replace all of these vectors with lines to form a triangle. And that triangle has sides of length v, because notice that v sub 0 and v sub 1 both have the same length because we're dealing with constant tangential speed, so these lengths are the same. So the two sides are length v, and the top is delta v. Now we're going to save this triangle for later. And now what we're going to do is we're going to take a look at the relationship between three quantities, chord, radius, and arc length, s. Set this up the same way we did with the previous vectors, defining angle that's swept out. And now we define chord length, which is just a line going between the 2 points in the motion. If we were to let the time between these 2 points shrink to 0, then we would also notice that chord length tends toward arc length. So chord length is really an approximation of arc length for what we're doing. Now we're going to move everything down as we did previously, and we're going to take a look at this geometry. And so looking at this shape, we have a new triangle, and that has side lengths of r and top of chord length. So now what we've done is we've built 2 triangles, so bringing back the old one. And we notice that these are similar triangles. And the rule for similar triangles, meaning triangles with identical angles inside, the rule for similar triangles, it says that the ratio of sides are equal. That means that chord over radius is equal to delta v over v. We're going to divide everything by delta t. We're going to take the limit as delta t tends towards 0. So we already know that chord length is going to approximate arc length. And we know that delta t, if we let it tend towards 0, it becomes this small differential quantity, just a tiny change in time, which is called dt. And so this gives us the equation shown on the right. And now we can rewrite the the arc length as speed times change in time. And so we rewrite arc length as v dt, and then we're going to simplify. And this final result is known as the centripetal or radial acceleration, and it's defined as v squared over r. V is our tangential speed. And we notice that centripetal acceleration points toward the center of rotation at all points in the motion. So anytime you're moving about a circular path, for instance, driving on a curved road, for instance, swinging a tetherball, whatever object is moving has an acceleration toward the center of the circle. This doesn't mean that it's moving toward the center of the circle. It means that its velocity vector is changing in a direction toward the center of the circle. So a little bit more on tangential speed and velocity. We're going to assume we're moving at a constant tangential speed around a circular path. And what we're asking is, how fast am I moving in the direction of motion at that instant? If my direction of motion is shown here, moving to the right at that instant, I can say my tangential speed here is 5 meters per second. That's how fast I'm going in the direction of motion. Now, if I wanted to find a tangential velocity, Now I'm talking about what is my speed in the direction of motion and what is my direction. Direction's constantly changing, so we can't really assign an I or a J component constant to every velocity vector. They're going to be changing, so our I and J components are constantly changing. Now we're going to find out that tangential speed is related to centripetal acceleration and to angular speed. So we already know that tangential speed is related to centripetal acceleration. Centripetal acceleration is v squared over r. And again, that points at toward the center of the circle at all times. Also, tangential speed is related to angular speed. Here, notice that the amount of angle being swept out corresponds to a certain speed around the circular path. So in this example, about pi over 4 radians are being swept out every 3/4 of a second. So that leads us to be able to calculate our angular speed average, which in this case is pi over 3 radians per second. So that value, pi over 3 radians per second, is delta theta delta t. So omega is delta theta delta t, and that's average. And now we're going to take a look at arc length, radius, and angle. So here's our arc length being swept out. And that's related to radius and angle, as we learned previously, as r delta theta. So our tangential velocity really is how much arc length are we sweeping out in a given time, how much ground are we covering, in other words, in the linear direction, and that could be defined as arc length over delta t. Now plugging in for what arc length is equal to, gives us r delta theta delta t. But what is delta theta delta t? It's omega average. So now we have a relationship between tangential speed and omega average. And now all we need to do is take the limit as delta t goes to 0. And we get our final result, which says that tangential speed is equal to r times omega. So what we've done is we've related tangential speed to angular speed here. Okay, now we can go a step further and we can relate centripetal acceleration to angular speed using just some simple algebra. So what we're going to do, we have these two equations so far. We've got a relationship between tangential speed and radial acceleration. We've got a relationship between tangential speed and angular speed. So juggling these around, we square the tangential speed equation, and we plug it in place of tangential speed on the left to get this equation, which is a relationship between centripetal acceleration and angular speed. And so here's the relationship. It's r omega squared. Now what we need to do is define tangential acceleration. This is something new that we haven't talked about. But if an object is moving in circular motion, it'll only have a tangential acceleration if it's changing speed along the direction of motion. So for instance, if you're rounding a curve in a car and you're speeding up or slowing down as you're going around the curve, then you're going to have a tangential acceleration. So please take time to think about this. If you're rounding a curve, you always have a radial acceleration, or acceleration due to the fact that your velocity is changing as a vector, changing direction. But you don't always have a tangential acceleration, meaning you're not speeding up or slowing down in the linear path that you're following. So if linear speed is changing, angular speed must also be changing. Makes sense. So as we speed up or slow down in our car, we're sweeping out more or less angle as we travel. So we have the relationship here on the right. Tangential acceleration is dvt, where v is tangential, so it makes sense. It's a change in speed with respect to time. We know that v is r omega, so we can plug in. And we know that r is a constant here because we're moving around a circular path with a constant radius. So we could pull that out of this differential, and we're left with r d omega dt. But what is d omega dt? It's a change in angular speed with respect to time, which is angular acceleration. So now we have our relationship. Tangential acceleration is equal to r alpha. And so it's a good idea to take time and go through this video, go through your book, and write out all of the different equations that we've learned. There's a few of them. They're very short, easy to use equations for solving problems. So what we're looking at here are really two acceleration components that are always at 90-degree angles to each other. We've got the tangential acceleration moving along the direction of our path, and we've got the radial acceleration that's moving at a 90-degree angle to our path. So we can actually add these vectors together to get a total acceleration vector. And we're going to do that in some example problems next class. So what we've done so far, and I'm going to change everything to capital R to match the picture, is we've defined a tangential acceleration and a radial acceleration. And the equations are shown on the bottom here. Here's a summary of what we've learned in this presentation. Okay, we've related angular and linear quantities. We've defined some quantities. One of the big quantities we've defined is tangential or linear velocity, which is a constantly changing vector when you're dealing with circular motion. And for most of what we're doing, it's going to have a constant magnitude or length of r times omega. We've also defined linear acceleration as two components for circular motion. One is the radial acceleration, which is calculated as omega squared r and always points toward the center of the circle. And the other is tangential acceleration, which may or may not be present depending on whether you're changing speeds in the direction of motion. And that's defined as r times alpha. So definitely go through this presentation, watch it a couple times if you need to, write down questions, write down all the equations that you know how to use or that you plan on using for homework. And please don't hesitate to contact me via email if you have any questions. And thank you for watching.